A very good day to everyone watching this video. My name is Eugene, and in this video, I'll be introducing to you two different technologies which are involving the concepts of electromagnetism, namely transmission lines and waveguides. So in this video, I'll give everyone a brief introduction to these two different technologies, and after that, I'll share some different types of these technologies as well as their applications in different scenarios. So let's begin with the first technology, transmission lines. So you may be wondering, how are they different from electric cables? Well, ordinary cables are fine for low frequency signals, such as mains power, which ranges in the 50 to 60 Hz frequency range, as well as audio signals, which range from 20 Hz to 20 kHz. However, when the frequency becomes extremely high, such as in the radio frequency range of 30 kHz, energy begins to be radiated off as radio waves, causing loss of efficiency. This is why we use transmission lines, which are a system of two or more conductors arranged to guide high-frequency electrical signals efficiently. The transmission line carries the signal and its return path in a controlled way to minimize loss, distortion, and interference. And by using impedance matching on the two different lines, they help to minimize signal reflections. So examples of transmission lines that we use are coaxial cables, twisted pairs, and microstrips. So as you can see on the images on the right, an ordinary electric cable has a central wire running through it, whereas a transmission line has an additional wire mesh going on the outside, which acts as a return path, helping to shield the main power line from any external interference. Now, let's move on to some different types of transmission lines, with the first one being the coaxial cable, which is a central wire carrying the signal and is surrounded by insulation and then a metal shield that blocks the interference. The central conductor carries the main signal, while the outer shield, which is normally made of wires, helps to prevent energy loss and external noise. The whole cable is then wrapped in another of insulation for protection. Normally, coaxial cables are used in TV, satellite, and internet connections. So as you can see in the images, we tend to use coaxial cables in a wide variety of applications, such as in splitters, antennas, TVs, satellites, modems, and set-top boxes for our TVs. And in the diagram below, we can see that the wire is made up of four different components, two of which carry current and the other two being insulators. Next, let's move on to the twisted pair, which reduces electromagnetic interference by pairing two different wires that carry forward and return signals. So as you can see from the picture, the two wires are actually twisted with one another so that the two different direction signals can cancel out each other. Sorry. And these pairs are normally used in Ethernet and telephone cables, as you can see on the image on the right. And the last one we are talking about is the microstrip line, which is a flat metal conductor printed on a circuit board with a ground plane beneath it. So what this means is that there's a central dielectric, as you can see on the green section in the image, and then there are two different metal conductors printed on the upper end and on the lower end of the dielectric. Printed circuit boards normally use microstrip lines in electronic devices. Now let's talk about waveguides. So waveguides are a hollow metal structure that guides EM waves, normally in the microwave frequency range. They work by bouncing EM waves inside the walls of the waveguides, helping to guide them with very low energy loss, distortion, or interference. So examples of these include rectangular waveguides, circular waveguides, and dielectric waveguides. So you may be wondering, what's the difference between transmission lines and waveguides? Well, transmission lines transmit signals via a current flowing through two conductors, with EM waves confined between them. However, for waveguides, they actually propagate the EM waves themselves through boundary reflections within a hollow or dielectric structure without a conduction current. So this may be likened to a sort of pipe where the EM waves are flowing through these pipes and they are bouncing off the walls till they reach their destination. Now, let's talk about rectangular waveguides, which are hollow metal tubes with a rectangular cross section. Because of their shape, they are efficient, meaning that they are able to handle high power with a low signal loss. Rectangular waveguides tend to be applied in radar systems, including those in the military, aviation, and weather industry, satellite communication, as well as microwave ovens. One example of this is on the image on the right, which has a military radar with a waveguide circled in red. Another example is in the microwave oven, where the microwaves are channeled into the microwave oven's cooking chamber to help heat food up. The next one is the circular waveguide, which is similar to the rectangular waveguide in that it is a hollow metal tube, but instead of being rectangular, it has a circular cross section. This makes it suitable for applications requiring rotational symmetry, as due to its shape, it supports circular polarization. This makes it useful for applications the where there are moving parts and which require the EM waves to maintain the same polarization. Some examples include in airport surveillance radar (ASR), satellite earth stations with rotating joints, as well as space communication systems, where a satellite may be moving around the earth and a radar would have to track it. So as you can see in the image below, this is the general structure of a circular waveguide with a hollow tube with some sort of either a vacuum or dielectric in the middle. Lastly, we now move on to the dielectric waveguide, which has a solid dielectric material printed onto a PCB, as mentioned before, or a chip. So, due to their size and easily availability for manufacturing, they can be compact and low cost. For dielectric waveguides, they are typically implemented in small circuit boards, such as in 5G devices for our smartphones or wireless chipsets, or in MMICs, otherwise known as monolithic microwave integrated circuits. In the image on the left, we can see how the dielectric is applied onto the metal chip so that EM waves can flow through them. And then in a larger scale, these are then used in different kinds of technologies, such as in the MMIC for the spacecraft applications shown on on the image below. And with that, I think I've reached the end of my video. Thank you everyone for watching, and I hope that you have found it informative in some way. Thank you.